You'll be surprised how often with continuous data, when you're collecting it, this bell-shaped distribution occurs. So this sort of pattern, okay, so this one's height in inches, and I've put into class intervals and come up with a histogram, but we can still see the pattern of the curve there. Right? So a bell-shaped distribution, what we're seeing is one where the mode, or modal class in this case, is somewhere in the middle of the data. The distribution is almost symmetrical. And the reality is, when you're dealing with real life figures, to get something perfectly symmetrical, geez, you might even be questioning your data if you got something that was perfectly symmetrical. But, you know, it has that sort of symmetrical shape to it. Now, the classic bell-shaped curve, where it is perfectly symmetrical, so it means the mean and the median and the mode, they'll all be the same thing. Now, ours is not, as we can see, symmetrical, but as I say, when you're dealing with real data, it's unusual to get something that's perfectly symmetrical. And the other thing with the bell-shaped curve is it tails off pretty quickly as you get out to the extremities. So those sort of features is a bell-shaped distribution. Now, we're really interested in what we call the normal distribution. There is the formula for the probability density function of a normal distribution. Isn't it a beautiful thing? So 1 over the standard deviation times the square root of 2 pi e to the power of minus x minus the average squared all over 2 times the variance. So yes, mu and sigma squared are standing for our mean and variance. Now, a notation we use to say the random variable is in normal distribution is simply something like that. We go x and then a tilde. N is saying, well, we know our random variable is in a normal distribution, and the two key features we want to know about that is what is the mean, what is the variance. So what are characteristics of this distribution? So it does turn out to be a perfectly symmetrical distribution. Those +1 and +2 and +3 there are representing how many standard deviations away from the mean those points are. And as it's symmetric, well, we know it's an even function. So function x is equal to function negative x. That's if I've centered it at 0 there. The maximum will be the average, but it'll also be the mode. It'll also be the median. And again, an even function, so it is symmetric about the average. Now here's another interesting feature of it. The points of inflection occur at the first standard deviation, either side. So that's where the point of inflection turns out to be. What is the standard normal distribution? Well, the standard normal distribution is actually the graph that I just put up. It's the one where the average is 0 and the deviation is 1. So if I had to find it with Z, we often use Z for the standard normal distribution, which is why we end up with Z scores. So Z, which is a normal distribution, and 0, 1, the two main features we want to know. What's the average? What's the variance? That means the formula now becomes, when we sub that information in, tidies up a little bit, 1 on the square root of 2 pi e to the power of minus z squared on 2. And you'll notice that the pronumeral we use for this is phi. That's a phi. Yeah, so phi z. So how do we calculate the probabilities then? Well, we integrate. Notice we now go to capital phi. So capital phi is the cumulative distribution function. So that's when we end up integrating. And the curve for that one, the cumulative distribution function, it also has a familiar pattern. Can anyone remember a problem we did where that ended up being the distribution, something that looked like that? It was last year. It was in Perms and Comms.
Oh, the birthday one.
The birthday problem, yeah. Yeah, it had that sort of, that pattern. Okay, now here's the thing about integrating. Now that's little phi, so we're talking about the probability density function. There's a little problem. Well, unfortunately, we can't do it. So capital phi z, so the cumulative, to express it with algebraic trig exponentials, all those little tricks that we have for integrating, it just doesn't work on this function. So it's not a big deal, because really I'm more interested in the definite integral rather than the indefinite integral. So really all we want to know is the value. and we can estimate the value using trapezoidal rules and things like that. But because it's a standard one, that's been worked out already, of course. We don't want to work it out time and time again, and that's why we have tables of values, and we can simply just look up what the value is. So something like that. That's a very compacted one. But so for instance, if I wanted to work out that where z is less than or equal to 0.25, which would be the cumulative for 0.25, we're going from negative infinity up to 0.25, and we just look at our table and go, well, there's 0.2 and there's 0.05, bingo. So the answer is 0.5987. Your tables, though, are only going for the positive numbers. Remember, our distribution also has negative numbers. So how do we use it? So that's fine. We know that phi z will be the probability of z is less than or equal to z. But if I wanted to work out phi of negative z, then it'll be 1 minus phi z because of the symmetry. We don't need the negatives. So phi negative z will be 1 minus phi z. If I wanted to work out z greater than or equal to z, then, well, that's going to be the same as phi negative z. Now, we're usually going to want to work out values, so we trap it in between two values. So it'll be phi z2 minus phi z1. And if we said the absolute value, because again we want to capture symmetry, so we're going between plus or minus, it would end up being 2 phi z minus 1, because you would have the phi of z minus the phi of minus z. So you've got phi z minus 1 minus phi z, you get the 2z. Which calculator do you have? Now becomes the question. If you have a 100 AU plus, mode 3, of course, put your calculator into statistics mode. Shift 1 5. So you get shift 1 5. That should bring up the standard normal distribution menu. You'll see some letters there. P, Q, R. There's another one there that we don't tend to use. But this is what it represents. P will give you phi z. So going from minus infinity up to a value. Q will give you from 0 up to a particular value. And R gives you the right-hand side when it's greater than a value. So, and I just looking at this realised I'm not saying 1 minus 0.25 here. If you choose option 1, which is the P, and you want to find 5.25, so you sub in 0.25, it should come up with 0.59871. And so you actually get them a little bit more accurate than the tables themselves. So let's play with our calculators, all the tables, see if you can come up with these. So we want z is less than or equal to 0.44. In fact, you might even want to check that the table, looking at the table, you do get the same thing. You should get 0.67003. If we want less than or equal to minus 0.81, the advantage of the calculator, we can just type in minus 0.81 and we don't have to manipulate it using the tables. And that should end up being, but if I had to use the tables, then I would go 1 minus the 0.81, and either way, well, I've used the calculator obviously because I've ended up with 5 decimal places there. 0.20897. If I want to go in between the two, so then it's 0.94 minus the minus 2.34, we should get 0.816748, being incredibly accurate. Using the tables again, you come up to 4 decimal places. If it was in between minus 1.15 and plus 1.15, using the tables, I'd go twice the phi 1.15 minus 1, and there we go, 0.74986. So that brings us to what's known as the empirical rule. There's our standard normal distribution and the different standard deviations away from the mean. Now, in our standard normal distribution, 68% of the data, well, in fact, not only the standard one, in any normal distribution, the 68% of the data should lie in the range plus or minus 1 deviation. And this is coming to where the z-scores are. So you get a z-score of 1, if you like. 95% of the data should be between plus or minus 2 deviations, 99.7%. So 16D.